Chapter 2, Potential Series and Exponential Function. A. General. Section 39, an expression such as y equals 1 divided by the quantity 1 minus x represents a fraction. This means it is the result of division. Like any fraction, it can be calculated, meaning the fractional form can be eliminated by dividing the numerator by the denominator as follows. 1 minus x is divided into 1, resulting in 1 plus x plus the square of x plus the cube of x, and so on. The first step is dividing 1 minus x into positive x. The second step involves dividing x minus the square of x into positive x squared. Finally, x squared minus the cube of x is divided into positive x cubed. Thus, the fraction y equals 1 divided by the quantity 1 minus x can also be expressed in the form y equals 1 divided by the quantity 1 minus x, which equals 1 plus x plus the square of x plus the cube of x, and so on. This is an infinite series composed of successive powers of x, also called a potential series. In the same way, by dividing through, the expression y equals 1 divided by the quantity 1 plus x can also be reduced to an infinite series. Y equals 1 divided by the quantity 1 plus x, which equals 1 minus x, plus the square of x minus the cube of x, and so on. This is a quick explanation of the long division process. The expression y equals 1 divided by the quantity 1 minus x is a fraction, where the numerator is 1 and the denominator is the quantity 1 minus x. We aim to convert this fraction into a series by performing long division, similar to how we divide numbers. First, divide the numerator, which is 1, by the denominator, the quantity 1 minus x. The process involves repeatedly dividing the remainder by the denominator. First division, divide 1, the numerator, by 1, the constant part of the denominator. The result is 1. The remainder is negative x. Second division, divide the remainder, negative x, by 1. The result is positive x. The remainder is x squared. Third division, divide the new remainder, x squared, by 1. The result is positive x squared. The remainder is negative x cubed. Fourth division, divide the new remainder, negative x cubed, by 1. The result is positive x cubed. The remainder is x to the power of 4. This pattern continues indefinitely, generating terms of the series 1 by 1. Each term corresponds to a higher power of x. For the fraction y equals 1 divided by the quantity 1 minus x, the result of the division is y equals 1 plus x squared plus x cubed, and so on. For the fraction y equals 1 divided by the quantity 1 plus x, a similar process gives y equals 1 minus x plus x squared minus x cubed, and so on. These series represent the fractional expressions in terms of powers of x, where the process of division systematically generates each term. The infinite series 2 or 4 is another form of representation of the expression 1 or 3, just as the periodic decimal fraction is another representation of the common fraction, for instance 0.6363 repeating equals 7 divided by 11. Section 40. As the series contains an infinite number of terms, in calculating numerical values from such a series, perfect exactness can never be reached. Since only a finite number of terms are calculated, the result can only be an approximation. By taking a sufficient number of terms of the series, however, the approximation can be made as close as desired. That is, numerical values may be calculated as exactly as necessary, so that for engineering purposes, the infinite series 2 or 4 gives just as exact numerical values as calculation by a finite expression, 1 or 3, provided a sufficient number of terms are used. In most engineering calculations, an exactness of 0.1% is sufficient. Rarely is an exactness of 0.01% or even greater required, as the unavoidable variations in the nature of the materials used in engineering structures and the accuracy of the measuring instruments impose a limit on the exactness of the result. For the value x equals 0.5, the expression 1 gives y equals 1 divided by the quantity 1 minus 0.5, which equals 2. While its representation by the series 2 gives y equals 1 plus 0.5 plus 0.25 plus 0.125 plus 0.06, 25 plus 0.03125, and so on. The successive approximations of the numerical values of y then are as follows. Using one term, y equals 1, which equals 1, and the error is negative 1. Using two terms, y equals 1 plus 0.5, which equals 1.5, and the error is negative 0.5. Using three terms, y equals 1 plus 0.5 plus 0.25, which equals 1.75, and the error is negative 0.25. Using four terms, y equals 1 plus 0.5 plus 0.25 plus 0.125, which equals 1.875, and the error is negative 0.125. Using five terms, y equals 1 plus 0.5 plus 0.25 plus 0.125 plus 0.0625, which equals 1.9375, and the error is negative 0.625. It is seen that the successive approximations come closer and closer to the correct value, y equals 2, but in this case always remain below it. That is, the series 2 approaches its limit from below, as shown in figure 24, in which the successive approximations are marked by crosses. For the value x equals 0.5, the approach of the successive approximations to the limit is rather slow. To get an accuracy of 0.1%, that is, to bring the error down to less than 0.002, requires a considerable number of terms. With such alternating approach of the series to the limit, as exhibited by series 4, the limiting or final value is between any two successive approximations. That is, the error of any approximation is less than the difference between this and the next following approximation. Such a series is thus preferable in engineering as it provides information on the maximum possible error, while the series with one-sided approach does not provide this information without special investigation. In the latter case, the error is greater than the difference between successive approximations. Section 42. Substituting x equals 2 into expressions 1 and 2, equation 1 gives y equals 1 divided by the quantity 1 minus 2, which equals negative 1, while the infinite series 2 gives y equals 1 plus 2 plus 4 plus 8 plus 16 plus 32, and so on. The successive approximations of the latter thus are as follows: 1, 3, 7, 15, 31, 63, and so on. That is, the successive approximations do not approach closer and closer to a final value. On the contrary, they get further and further away from each other and give entirely wrong results. They give increasing positive values, which apparently approach infinity for the entire series, while the correct value of the expression by equation 1 is y equals negative 1. Therefore, for x equals 2, the series 2 gives unreasonable results and thus cannot be used for calculating numerical values. The same is the case with the representation 4 of the expression 3 for x equals 2. The expression 3 gives y equals 1 divided by the quantity 1 plus 2, which equals 0.3333, repeating, while the infinite series 4 gives y equals 1 minus 2 plus 4 minus 8 plus 16 minus 32, and so on, and the successive approximations of the latter thus are 1, negative 1, positive 3, negative 5, positive 11, negative 21, and so on. Hence, while the successive values still are alternately above and below the correct or limiting value, they do not approach it with increasing closeness, but more and more diverge therefrom. Such a series, in which the values derived by the calculation of more and more terms do not approach a final value closer and closer, is called divergent, while a series is called convergent if the successive approximations approach a final value with increasing closeness. Section 43. While a finite expression, as 1 or 3, holds good for all values of x, and numerical values of it can be calculated, whatever may be the value of the independent variable x, an infinite series, as 2 and 4, frequently does not give a finite result for every value of x, but only for values within a certain range. For instance, in the above series for negative 1 less than x less than positive 1, the series is convergent, while for values of x outside of this range, the series is divergent and thus useless. When representing an expression by an infinite series, it thus is necessary to determine that the series is convergent, that is, approaches with increasing number of terms a finite limiting value, otherwise the series cannot be used. Where the series is convergent within a certain range of x, divergent outside of this range, it can be used only in the range of convergency, but outside of this range, it cannot be used for deriving numerical values, but some other form of representation has to be found, which is convergent. This can frequently be done, and the expression thus represented by one series in one range and by another series in another range. For instance, the expression 1, y equals 1 divided by the quantity 1 plus x, by substituting x equals 1 divided by u, can be written in the form y equals u divided by the quantity 1 plus u. And then developed into a series by dividing the numerator by the denominator, which gives y equals u minus u squared plus u cubed minus u to the power of 4, and so on. Or resubstituting x, y equals 1 divided by x minus 1 divided by x squared plus 1 divided by x cubed minus 1 divided by x to the power of 4, and so on, which is convergent for x equals 2. And for x equals 2, it gives y equals 0.5 minus 0.25 plus 0.125 minus 0.0625, and so on, with the successive approximations 0.0.5, 0.25, 0.375, 0.3125, and so on, which approach the final limiting value y equals 0.333 repeating. Section 44. An infinite series can be used only as convergent. Mathematical methods exist for determining whether a series is convergent or not. For engineering purposes, however, these methods usually are unnecessary. For practical use, it is not sufficient that a series be convergent, but it must converge so rapidly, that is, the successive terms of the series must decrease at such a great rate, that accurate numerical results are derived by the calculation of only a very few terms, 2 or 3, or perhaps 3 or 4. This, for instance, is the case with the series 2 and 4 for x equals 0.1 or less. For x equals 0.5, the series 2 and 4 are still convergent, as seen in 5 and 7, but are useless for most engineering purposes, as the successive terms decrease so slowly that a large number of terms have to be calculated to get accurate results. And for such lengthy calculations, there is no time in engineering work. If, however, the successive terms of a series decrease at such a rapid rate that all but the first few terms can be neglected, the series is certain to be convergent. In a series, therefore, in which there is a question whether it is convergent or divergent, as for instance the series y equals 1 plus 1 divided by 2 plus 1 divided by 3 plus 1 divided by 4 plus 1 divided by 5 plus 1 divided by 6, and so on, which is divergent. Or y equals 1 minus 1 divided by 2 plus 1 divided by 3 minus 1 divided by 4 plus 1 divided by 5 minus 1 divided by 6, and so on, which is convergent. The matter of convergency is of little importance for engineering calculation, as the series is useless in any case, that is, does not give accurate numerical results with a reasonably moderate amount of calculation. A series, to be usable for engineering work, must have the successive terms decreasing at a very rapid rate, and if this is the case, the series is convergent, and the mathematical investigations of convergency thus usually become unnecessary in engineering work. Section 45. It would rarely be advantageous to develop such simple expressions as 1 and 3 into infinite series such as 2 and 4, since the calculation of numerical values from 1 and 3 is simpler than from the series 2 and 4, even though very few terms of the series need to be used. The use of the series 2 or 4 instead of the expressions 1 and 3 therefore is advantageous only if these series converge so rapidly that only the first two terms are required for numerical calculation, and the third term is negligible, that is, for very small values of x. Thus, for x equals 0.01, according to 2, y equals 1 plus 0.01 plus 0.0001, and so on, which equals 1 plus 0.01. As the next term, 0.0001, is already less than 0.01% of the value of the total expression. For very small values of x, therefore, by 1 and 2, y equals 1 divided by the quantity 1 minus x, which equals 1 plus x, and by 3 and 4, y equals 1 divided by the quantity 1 plus x, which equals 1 minus x. And these expressions 10 and 11 are useful and very commonly used in engineering calculation for simplifying work. For instance, if 1 plus or minus a very small quantity appears as a factor in the denominator of an expression, it can be replaced by 1 minus or plus the same small quantity as a factor in the numerator of the expression, and inversely. For example, if a direct current receiving circuit of resistance R is fed by a supply voltage E sub 0 over a line of low resistance R sub 0, what is the voltage E at the receiving circuit? The total resistance is R plus R sub 0. Hence, the current I equals E sub 0 divided by the quantity R plus R sub 0. And the voltage at the receiving circuit is E equals R times I, which equals E sub 0 multiplied by the fraction R divided by the quantity R plus R sub 0. If now R sub 0 is small compared with R, it is equals E sub 0 multiplied by the fraction 1 divided by the quantity 1 plus the fraction R sub 0 divided by R, which equals E sub 0 multiplied by the quantity 1 minus the fraction R sub 0 divided by R. As the next term of the series would be the square of the fraction R sub 0 divided by R, the error made by the simpler expression 13 is less than the square of the fraction R sub 0 divided by R. Thus, if R sub 0 is 3% of R, which is a fair average in interior lighting circuits, the square of the fraction R sub 0 divided by R equals 0.03 squared, which equals 0.0009, or less than 0.1%. Hence is usually negligible. Section 46. If an expression in its finite form is more complicated and thereby less convenient for numerical calculation, as for instance if it contains roots, development into an infinite series frequently simplifies the calculation. Very convenient for development into an infinite series of powers or roots is the binomial theorem. The quantity 1 plus or minus u raised to the power n equals 1 plus or minus n times u, plus the fraction n times the quantity n minus 1 divided by 2 multiplied by u squared, plus or minus the fraction n times the quantity n minus 1 times the quantity n minus 2 divided by 3, multiplied by u cubed, and so on, where m equals 1 times 2 times 3, and so on up to m. Thus, for instance, in an alternating current circuit of resistance R, reactance X, and supply voltage E, the current is I equals E divided by the square root of the sum of R squared and X squared. If this circuit is practically non-inductive, as in an incandescent lighting circuit, that is, if X is small compared with R, equation 15 can be written in the form I equals E divided by the product of R and the square root of 1 plus the square of the fraction X divided by R, which equals E divided by R multiplied by the quantity 1 plus the square of the fraction X divided by R raised to the power of negative 1/2. And the square root can be developed by the binomial theorem 14. Thus, let U equal the square of the fraction X divided by R, and let n equal negative 1/2, which gives the quantity 1 plus the square of the fraction x divided by r, raised to the power of negative 1/2 equals 1 minus 1/2, multiplied by the square of the fraction x divided by r, plus 3/8 multiplied by the fourth power of the fraction x divided by r, minus 5/16 multiplied by the sixth power of the fraction x divided by r, and so on. In this series 17, if x equals 0 times r or less, that is, the reactance is not more than 10% of the resistance, the third term, 3/8 multiplied by the fourth power of the fraction x divided by r, is less than 0.01% and hence negligible. The series is approximated with sufficient exactness by the first two terms. The quantity 1 plus the square of the fraction x divided by r raised to the power of negative 1/2 equals 1 minus 1/2 multiplied by the square of the fraction x divided by r, and equation 16 of the current then gives I equals E divided by r multiplied by the quantity 1 minus 1/2 multiplied by the square of the fraction x divided by r. This expression is simpler for numerical calculations than the expression 15, as it contains no square root. Section 47. Development into a series may become necessary if further operations have to be carried out with an expression for which the expression is not suited, or at least not well suited. This is often the case where the expression has to be integrated, since very few expressions can be integrated. Expressions under an integral sign therefore very commonly have to be developed into an infinite series to carry out the integration. Example 1. Of the equilateral hyperbola, as shown in figure 26, x times y equals a squared. The length L of the arc between x sub 1 equals 2 times a and x sub 2 equals 10 times a is to be calculated. An element dl of the arc is the hypotenuse of a right triangle with dx and dy as the two cathetes. It therefore is dl equals the square root of the sum of dx squared and dy squared, which equals the square root of the sum of 1 and the square of the fraction dy divided by dx multiplied by dx. As shown in figure 26 of the equilateral hyperbola and from equation 20, y equals a squared divided by x, and dy divided by dx equals negative a squared divided by x squared. Substituting equation 22 into equation 21 gives dl equals the square root of the sum of 1 and the fourth power of the fraction a divided by x multiplied by dx. Hence, the length L of the arc from x sub 1 to x sub 2 is L equals the integral from x sub 1 to x sub 2 of dl, which equals the integral from x sub 1 to x sub 2 of the square root of the sum of 1 and the fourth power of the fraction a divided by x multiplied by dx. Substituting the fraction x divided by a equals v, that is dx equals a times dv, and also substituting v sub 1 equals the fraction x sub 1 divided by a, which equals 2, and v sub 2 equals the fraction x sub 2 divided by a, which equals 10, gives L equals a times the integral from v sub 1 to v sub 2 of the square root of the sum of 1, and the fraction 1 divided by v to the power of 4 multiplied by dv. The expression under the integral is inconvenient for integration. It is preferably developed into an infinite series by the binomial theorem 14. Let u equal the fraction 1 divided by v to the power of 4, and n equal 1/2. Then the square root of the sum of 1 and the fraction 1 divided by v to the power of 4 equals 1 plus 1/2 times the fraction 1 divided by v to the power of 4 minus 1/8 times the fraction 1 divided by v to the power of 8 plus 1/16 times the fraction 1 divided by v to the power of 12 minus 5 over 128 times the fraction 1 divided by v to the power of 16, and so on. And L equals a times the integral from v sub 1 to v sub 2 of the quantity 1 plus 1/2 times the fraction 1 divided by v to the power of 4 minus 1/8 times the fraction 1 divided by v to the power of 8 plus 1/16 times the fraction 1 divided by v to the power of 12 minus 5 over 128 times the fraction 1 divided by v to the power of 16, and so on, multiplied dv. This simplifies to L equals a times the quantity v, multiplied by the series 1 minus the fraction 1 divided by 2 times 3 times v to the power of 4, plus the fraction 1 divided by 7 times 8 times v to the power of 8, minus the fraction 1 divided by 11 times 16 times v to the power of 12, plus the fraction 1 divided by 3 times 128 times v to the power of 16, and so on, evaluated from v sub 1 to v sub 2. Further simplification gives L equals a times the series where the terms are v sub 2 minus v sub 1, plus the fraction 1 divided by 6, multiplied by the difference of the fractions 1 divided by v sub 1 cubed minus 1 divided by v sub 2 cubed minus the fraction 1 divided by 56, multiplied by the difference of the fractions 1 divided by v sub 1 to the power of 7 minus 1 divided by v sub 2 to the power of 7, plus the fraction 1 divided by 176, multiplied by the difference of the fractions 1 divided by v sub 1 to the power of 11 minus 1 divided by v sub 2 to the power of 11, and so on. Substituting the numerical values, L equals a times the series where the terms are 10 minus 2 plus the fraction 1 divided by 6, multiplied by the difference 0.125 minus 0.001, minus the fraction 1 divided by 56, multiplied by the difference 0.0078 minus 0, plus the fraction 1 divided by 176, multiplied by the difference 0.0001 minus 0. This simplifies to L equals a times the quantity 8 plus 0.0207 minus 0.0001, which equals 8.02206 times a. As seen, in this series, only the first two terms are appreciable in value. The third term is less than 0.01% of the total, and hence negligible. Therefore, the series converges very rapidly, and numerical values can easily be calculated by it. For x sub 1 less than 2 times a, that is v sub 1 less than 2, the series converges less rapidly and becomes divergent for x sub 1 less than a or v sub 1 less than 1. Thus, this series 17 is convergent for v greater than 1, but near this limit of convergency it is of no use for engineering calculation as it does not converge with sufficient rapidity. It becomes suitable for engineering calculation only when v sub 1 approaches 2. Example 2. Section 48. The logarithm of 1 equals 0, and therefore the logarithm of the quantity 1 plus x is a small quantity, if x is small. The logarithm of the quantity 1 plus x shall therefore obtain a series of powers of x, which permits its rapid calculation without using logarithm tables. It is the logarithm of u equals the integral of du divided by u. Then, substituting the quantity 1 plus x for u gives the logarithm of the quantity 1 plus x equals the integral of dx divided by the quantity 1 plus x. From equation 4, the fraction 1 divided by the quantity 1 plus x equals 1 minus x plus x squared minus x cubed, and so on. Hence, substituted into equation 24, the logarithm of the quantity 1 plus x equals the integral of the quantity 1 minus x plus x squared minus x cubed, and so on, multiplied by dx, which equals the integral of dx minus the integral of x multiplied by dx plus the integral of x squared multiplied by dx minus the integral of x cubed multiplied by dx, and so on, which equals x minus the fraction x squared divided by 2 plus the fraction x cubed divided by 3 minus the fraction x to the power of 4 divided by 4, and so on. Hence, if x is very small, the fraction x squared divided by 2 is negligible, and therefore all terms beyond the first are negligible. Thus, the logarithm of the quantity 1 plus x equals x. While, if the second term is still appreciable in value, the more complete but still fairly simple expression can be used. The logarithm of the quantity 1 plus x equals x minus the fraction x squared divided by 2, which equals x multiplied by the quantity 1 minus the fraction x divided by 2. If instead of the natural logarithm as used above, the decimal logarithm is required, the following relation may be applied. The logarithm base 10 of a equals the logarithm base 10 of epsilon multiplied by the logarithm base epsilon of a, which equals 0.4343 multiplied by the logarithm base epsilon of a. The logarithm base 10 of a is expressed by the logarithm base epsilon of a, and thus equations 19, 20, and 21 assume the form the logarithm base 10 of the quantity 1 plus x equals 0.4343 multiplied by the quantity x minus the fraction x squared divided by 2 plus the fraction x cubed divided by 3 minus the fraction x to the power of 4 divided by 4, and so on. Or, approximately, the logarithm base 10 of the quantity 1 plus x equals 0.4343 multiplied by x, or, more accurately, the logarithm base 10 of the quantity 1 plus x equals 0.4343 multiplied by x multiplied by the quantity 1 minus the fraction x divided by 2. Section B.